Alright, so let's move on to the second group of problems, which is numbers 6 through 10. So I think I'm going to do number 6. Number 6 says that we have 3 amps flowing through a loop that has a specific diameter. I'm going to draw it in 2D. Actually, it might be, here's the picture. So what I have is a loop, and the current flows through this thing. And the current is 3 amps. And of course, if there's a current, then there's a magnetic field set up everywhere. But let's determine the direction of the magnetic field at the center first. So what I have is, well, let's do it here. So the magnetic field, the current I points to the right. Take the thumb of your right hand, make it point in the same direction as this current here. Curl your fingers and you will see that the magnetic field comes out of the center of the loop, loops around, and then goes back in under here. Right, then if you were to go up here, then the current points in this direction. So take the thumb of your right hand, make it point in the same direction in which this arrow here points, and then curl your fingers of the right hand, and then you would see that the magnetic field comes from out of the center, loops around, and then comes back down on the outside of the loop. And you could do the same thing here if you wanted to, but I think we'll stop here. So what I have is that the magnetic field comes out of the page on the inside of this loop. I'm going to indicate that with by simply doing this. Point, circle. Magnetic field points out of the page at the center of the loop. And of course on the outside it points into the page, so it points into the page on the outside. Bunch of X's. Now the radius here is given to me, R. And that R is, well, actually what's given to me is the diameter. So that if the diameter is 10 centimeters, then the radius must be 5 centimeters, and that implies it's 0.05 of a meter. So I have the radius, and I can now calculate the value or the magnitude of the magnetic field at the center of this by using proper equation. So the equation for the magnetic field at the center of the loop is mu naught times the current divided by 2R. Well, let's plug in the numbers. So mu naught is 4 pi times 10 to the negative 7th times the current, which in this case it's 3 amps, divided by 2 times 0.05. Alright, so I guess I'm going to use my calculator to figure this one out. So let's see, this implies that the magnetic field at the center equals 3.8 times 10 to the minus 5th Teslas. So that's number 6. Now you should do number 7. So pause the video and then look at number 7, see if you can figure out number 7. And after that, you can continue with the video. I'm going to do 8 or 9. I'm going to do number 8. So here's number 8. All right, so what I have is, I have 2 loops, one above the other. How should I draw this so that this actually is not to do? Are they? Let's see, if they're a different diameter, then it'll be easy. I'll draw it in 2D. So one of them is 20 centimeters and the other one is, oh, I can't see it. Loop. Oh, I see. Okay. Yeah, one is bigger and smaller. All right, so I have 2 loops. Here's one. Draw it like this, and here's the other one. Draw it like this. So the smaller one is 2 centimeters. It's the radius of the smaller one is 1 centimeter. So let's label this as R1, and then let's state here R1 equals 1 centimeter, and then the radius of the bigger one, R2, is 20 centimeters. So 10 centimeters is the radius, and that would imply it's 0.1 of a meter, and this is 0.01 of a meter. Okay, and now let's see, what do they say about the currents flowing through it? So I have 2 amps flowing through this one. I don't think, okay, so this I1, let's state what this I1 is. So I1 is 2 amps. Oh, they both flow in the same direction clockwise. Oh, look at that. I actually got lucky with the direction. So they both flow clockwise. So this is I2, and I2 is 3 amps. Let's make sure we have the numbers right. Oh, wait. Yeah, okay. So 2 amps is on the inside, and I have 3 amps on the outside. It's 20 centimeters, so 10 centimeters for the radius, and 2 centimeters, 1 centimeter. That's good. Find magnetic field at the center. All right, so what I have is 2 loops. Each one produces a magnetic field at the center. In other words, the total magnetic field, which is what I'm after, the total magnetic field at the center is going to be the magnetic field produced by the first current plus the magnetic field produced by the second current. And let me put this in a vector form, because perhaps I'll have to actually subtract them. So let's figure this out. Do I subtract them or do I add them? So the magnetic field set up by I1. Let's draw this I1 in blue. All right, now if I1 points in this direction, then let's determine how the magnetic field points through the center. So take the thumb of your right hand, make it point in the same direction in which this current points, and then curl your fingers, and you will see that your fingers curl like this, meaning that the magnetic field due to current I1 points into the page at the center. So B1 points into the page. B1. All right, now let's do the other one in red. So I2 points in this direction, and you might see that we will get the same result, but take the thumb of your right hand, make it point in the direction of this current, and then curl your fingers, and you will see that the magnetic field due to this current comes from under the wire, all the way around, and then points into the page at the center. So I'm going to put X in red at the center, and I'm going to label this with B2. Both of the magnetic fields point in the same direction at the center, therefore I just have to add their magnitudes. So the total magnetic field at the center is just going to be B1 plus B2. And then let's substitute the actual equation for this. So for the circle, it's mu naught times I1 over 2 R1 plus mu naught times I2 over 2 R2. And so I guess what I could do here is I could take out mu naught over 2, then times the first current I1 was 2 amps divided by R1, which was 0.01, plus I2, that was 3 amps divided by 10 centimeters, so 0.1. Okay, and then we will get something out of this. So the magnetic field at the center, total magnetic field at the center is going to be, well, let's calculate this. I'm going to pause the video and figure this one out. And so it is 1.4 times 10 to the minus 4th Teslas. This is number 8. And now you should pause this video, and you should do numbers, we did 7, so do numbers 9 and 10. And in the meantime, I'm going to move on, and I think I'm going to do one of the last 3 problems. All right, I have cleared up the page a little. Let's look at number 11. So we have a solenoid. Let's draw a picture of a solenoid. Here's a solenoid. It's one wire that is looped into a coil, and then the current I flows in, and then the same current I flows out of it. And the current is 1.5 amps, and we have 100 turns. So big N, I guess I'll use big N. Big N is 100 turns, although I think I used little n before. Anyways, big N is 100 turns. And the length of this solenoid, so the length of this solenoid is this, is 10 centimeters, 15 centimeters. That would imply it's 0.15 of a meter. And in order for units to work out, we have to be in meters. Calculate the strength of the magnetic field on the inside of the solenoid. All right, so what I'm looking for is the magnetic field on the inside. Now the magnetic field points on the inside, just points like this. Whether it points to the right or to the left, it's hard to say from the picture, the way I drew it. Depending on how the current actually runs, the magnetic field could point to the right or to the left, but let's just say it points to the right. Now remember that for the solenoid, we make the assumption that the magnetic field is, it's true to a good extent, that the magnetic field is constant everywhere on the inside and it just points linearly in one direction. In reality, it wobbles a little as you get closer to the actual wire. But anyways, so the magnetic field on the inside, the equation for that is, well, you have two. So you have mu naught times n over L times I. And this would do, because you have mu naught, you know n, you know L, you know I. You just plug in the numbers and you get your answers. Let me just point something out. N prime is the density of the loops. In this case, it would be 100 loops divided by 0.15. This would be the density of the loops. You would have number of loops per meter. I think numbers 12 and 13 give you n prime. Okay, so that was hint for numbers 12 and 13. Now, let's plug in the numbers here. Mu naught, that's 4 pi times 10 to the minus 7th times the number of loops, which in this case is 100. Divided by the length, which is 0.15, and then times the current, which is 1.5. All right, and so we get something out of it. Whatever we get is whatever we get. Well, let's calculate this. Let's see what we get for this thing. So we get for this 1.3 times 10 to the minus 3rd Teslas. That's the magnetic field on the inside of the solenoid. All right, and then you should do numbers 12 and 13, and this way you know how to use all three of these equations. This one, and this one. And just remember that for the solenoid, the magnetic field is, in reality, it does something like this. Ooh, which makes me think of something. Anyways, the magnetic field is the strongest on the inside. It's weak on the outside, and the farther away you go from the solenoid, the weaker it gets. But this problem 11 actually also asked for the magnetic field on the outside. So this was the magnetic field on the inside. The magnetic field on the outside is, roughly speaking, 0. That's just the approximation we will use for all of this class. If you look at the problems here on the bottom, these are problems from the textbook for algebra-based physics, so 1202. And this is a problem for the calculus-based physics, that would be 1402. I think I may solve one or two of these problems here because I think they may be interesting, but I'm not sure yet. We'll see.